begin. So we're right in the middle of this Neyman-Pearson proof. Basically, Neyman-Pearson says for this simple versus simple case that test statistics that come out of the likelihood ratio test. So if you look at the likelihood ratio test stat and you calibrate it so that the type 1 error rate is alpha, it will be uniformly most powerful. So that means what I'm saying is that in the alternative space, the power will be higher than any other test across the whole spectrum of theta. So that's the uniform part. So across the whole spectrum of theta, the power of the test will be higher, and the probability of rejecting in the alternative space will be higher than any other test out there. So that's kind of like that. Keep in mind that what we're talking about is the simple versus simple test. Theta is equal to theta naught versus theta is equal to theta 1. I don't think there's any big controversy in this test setup. This can be extended to the one-sided case. We'll show that. But it will not be quite extendable to the sharp testing case. And we'll need another constraint in the system. And that's going to be, we're going to constrain our test to be unbiased. And we'll say a little bit about that. But what it ultimately does is it makes this thing right here, this condition, non-monotonic in the two-sided case. In the one-sided case, we want everything to be monotone because we're using the rule like it's monotone. It's only one-sided, this thing. So you can kind of see that this will be extendable to one-sided cases as we end up increasing theta 1, then we know what happens in these things, likelihood functions, as we increase them. I'll say a little bit more for you to draw a picture. I'll give you an example pertaining to the one-sided case. I'll tell you a little bit about p-values as well. So it's basically the thing that people use when they're talking about Neyman-Pearson. So p-values, of course, for the probability of the work stream data given that the null hypothesis is true. And so basically it's equivalent to this thresholding condition. So instead of finding k that calibrates your test in the null space, people usually map this over to a p-value. And it's all equivalent to each other. It's 1 to 1. So let's get started with this. So last time we showed that for our test, so this is going to be the test conforming to this condition. This is the likelihood ratio test stat. It's equivalent to that. And the book was really kind to you by changing everything in the problem setup. So instead of looking at the likelihood ratio test stat, instead of dividing by the maximum likelihood estimator, they constrained it to the alternative hypothesis. There's a problem in the book that walks you through that I assigned you for homework that says that the likelihood ratio test stat is equivalent to the condition of instead of dividing by the maximum likelihood estimator, the maximum likelihood, you end up constraining it just to the alternative space. And there's a one-to-one relationship between those two things. And then they flip the condition upside down. So instead of thresholding by looking at the null over the alternative, they flipped it around to look at the alternative over the null, and they flipped this sign around. So they did two things to you to confuse you. But you can think your way through it, and once you understand that all of these things are equivalent to each other, then I'll think you understand it. Okay. If you have any trouble with this, I'll be on for Thursday for review session. I can answer questions about the midterm there, any confusions that are arising. Okay, so last time we showed that the indicator pertaining to this test, so if this thing is 1, then we reject it. So this is a rejection indicator right here. Last time we showed that delta x is uniformly most powerful. And calibrate it to, in the null hypothesis, the power is alpha. So, and size alpha. This time we're going to show that if there is a uniformly most powerful test, it's this one. So we'll show if a UMP test exists, it's delta x. There is no other test that does this. That's kind of nice. We're going to just kind of unravel the proof that we worked through last time. Let me write it over here. So from last time we showed this is true. Delta x minus delta star, and I'll remind you what these things are, times f x given theta 1 minus k f x given theta naught. And I'll integrate over x that this thing is greater or equal to 0. So let me just remind you what these things are. So we're going to start out. We're going to say this is a UMP test of size alpha. We're going to let this be a size alpha test. What we're going to show is that delta star is also delta x. So we're going to say this is a size alpha test, and we're going to assume that it's also UMP. So assume it's UMP. So this is some test pertaining to this right here. This is that test. And now we're going to consider another test. So this is the typical mathematical trick to show uniqueness of something. Is we're going to state that something exists, then we're going to assume that there's another one out there, another test that has this property, and then we'll prove that those tests are identical to each other. So that's how a mathematician always proves uniqueness. So show one exists, assume one exists, assume there's another thing out there, and then show that they have to be the same. This is still true from last time. So I've got a UMP test, and this is true irregardless of this thing so long as it's size alpha, or if it's level alpha, this condition is also going to be true. And we verified that just by considering every case where delta x is a 1 or a 0, and then we consider every case where delta star x could be a 1 or a 0. We showed that this thing is always positive. So because they're both size alpha, I know a few things about this. I know that this means that our power function for theta naught, this is going to be the power, in the null space under theta naught for delta x. And we know what this is because it's size alpha. So that's equal to alpha. This one's also size alpha. So its power function is also equal to that. So we're starting with that. In a second, we're going to show this inequality is actually an equality. We'll see that in just a second. So this thing here 0 is going to bound our power function, theta 1, minus our power function for our other test, minus k times our power function, theta naught. This is a star. So we worked through and we showed that this integral breaks into 4 power functions. So probability of rejection. These are expectations. You might recognize every element in this integral as an expectation of an indicator. So it's the probability of that indicator. So it's the probability of rejection under the different hypotheses, the null and the alternative, and that's what the power function is. So I know a little bit about this. This is equal to alpha. This is equal to alpha. So this thing is 0. What can we say about this? Maybe we jump the gun. What can we say about this? They're both 0. So we'll analyze that in a second. How do we know this is 0?
Because it's UMP, we also.
UMP. So these are both UMP. So this is 0. They both have the same power. They're both UMP. They're both uniformly most powerful. So we're just left with this right here. I can flip around this inequality if you want. So beta 0, beta 0, minus beta star, beta 0. This is going to be greater than 0 right here. So once I take out the minus k, keep in mind k was positive, this is going to be less than or equal to 0. So these are both of size alpha. So this is also 0. That's alpha minus alpha. So that's also equal to 0. So this function is 0. Now, the measure theorists in the room might say, this might be non-zero on an unmeasurable set. And for those of you that are thinking that, you're right. No big deal. So we'll just look back at this inequality right here. So this thing right here, we just showed is equal to 0. So if this thing is equal to 0, then it means this thing right here has to be 0. That's not necessarily 0 right there. So if this is not necessarily 0, this is the thing that has to be 0. Now we're integrating over this space on x. So there could be a point where this is non-zero. But if you integrate over something that's a point, it doesn't give any mass. There's no measurement there. So that's what we mean when we say that this might not be equal to each other on an unmeasurable set. So let me just write that down. Delta x is equal to delta star x, except on a space that you cannot measure. jump away from each other, but just at a point. And if I'm integrating over something, it doesn't matter what happens at points, it matters what happens on intervals. So this is going to be a 0 on every interval that you decide to integrate over by anything you want to measure. So that's it. That's Neyman-Pearson. So they did a good job. So they were trying to give meaning to something that Fisher was doing. So Fisher was talking about p-values and computing the probability of more extreme data under the Null Hypothesis, and Neyman and Pearson wanted to know what it meant. What is that? Fisher said that's evidence against the Null Hypothesis. And Neyman and Pearson tried to think about this a little bit. What do you mean evidence? So they calibrated error rates with all of this. So Neyman and Pearson came in and said what Fisher was doing was equivalent to this, right here. So very equivalent to the thing where you say, I'm going to pick alpha to be 0.05 if your p-value falls under 0.05 reject. And it's equivalent to this, but you had to pick that error rate to start with. So alpha is the type 1 error. And it's all equivalent to this stuff right here. We'll look at an example in a second and show how to compute everything. Fisher didn't like it. So because he said you had to pick alpha a priori. So before you do anything, you have to fix alpha as your threshold. And that's going to be the error rate. Why Fisher didn't like that is because he was a rational human being and he knew how human beings would act. Okay, maybe he's not rational. So semi-rational. He at least thinks about a lot of stuff. And he didn't want to pick alpha up front. He knew nobody was going to do it. So he wanted to use the p-value itself as the evidence against the null hypothesis. Unfortunately, mathematically, he is incorrect. But Neyman and Pearson are mathematically correct, but it's hard to use this stuff. Now, I will say if you're working in an industrial factory and you get to repeat the experiment over and over and over again, you can monitor error rates. And you can say, for maybe good economic reasons, what's an error that you're willing to handle? What can you afford? How many mistakes can you make? If everybody makes mistakes, it's going to happen. So what can you afford to make? You might be able to use this setup in those cases, but in a scientific study, you're not doing things over and over and over again. You're usually doing it once. You have one sample. And so you're not repeating. So it's not the frequentist setup that Neyman and Pearson are proposing. To Neyman and Pearson's credit, they're mathematically correct about all of this. It seems like a good idea, and they never used this technique. So they never went ahead and did it in the first place. So you can't find an example of that happening. Saying that, everybody thought this is really great. Let's just use it, and let's abuse it. Let's look at an example. Something that we're familiar with. Kind of map this to what people do in Stat 101. Your first stat class that you ever took, when they taught you about a p-value, probably did something like this. So let's try to fill in the details from Stat 101. For example, we're going to look at this example. Right here, the one-sided case, where our data are going to come from a normal distribution with mean theta and variance sigma squared. And we'll say that sigma squared is known. If you don't know it, you're going to switch from the C test to the T test, and you're going to estimate sigma squared. And nothing changes in what I'm saying, except for which distributions you're going to use to measure everything. So I'm going to say this is known. Everything's IIE. And we're going to get n samples. So our likelihood ratio test stat, we can form, instead of doing that the way they did in the book, I'm going to use this new definition we found. So we'll look at this criteria. You can convince yourself, if you did a likelihood ratio test stat the way we first discussed it, we will get exactly the same answer. So nothing will change. I encourage you to check that out. So we're going to look at f of x. And this is our entire sample. given theta 1 over fx given theta naught. This is going to be greater than k. We'll have to calibrate this and show what k is. Usually we transform this thing into another constant. I'll show you what I mean in a second. So I can write this down and write down what this joint distribution is. This is going to be a ratio. Everything's IID. So I just product everything together so that I get joint sampling distribution. And then we're going to think about it as a function of theta, i.e. we're going to map everything over to a likelihood. So this is going to look like 1 over root 2 pi sigma e to the minus 1/2 xi's minus theta squared over sigma squared over n. And this is going to be theta 1 upstairs. So if we were doing the likelihood ratio test stat, we would be taking maximums, but because we're working in the simple versus simple case, i.e. just considering 1 theta 1 in a second, I will impose this constraint right here. But we're just plugging in a value right now. So e to the minus 1/2 xi's minus theta naught squared over sigma squared over n. So if you're working with a likelihood ratio test stat, you write down this same test statistic. And a lot of things cancel in all of this, and it's a bit of a mess because I have a product. Let me show you something real quick. They show this in the book. So instead of doing this, I'm going to use my sufficient statistic. So let's use some sufficient statistics. So anytime I'm working with my sampling function, I can also work with the sampling function of the sufficient statistic. And I can also use the minimal sufficient statistic and plug it all in. I'll let you verify that for yourself. But there is an argument in the proof in the book, and they prove something about this. So there's a formal proof, and I'll let you guess how they prove this at the end of the day. This is equivalent to 1 over root 2 pi sigma over root n. Just write out the whole thing, e to the minus 1/2 x bar minus theta 1 squared over sigma squared over n. 1 over root 2 pi sigma over root n e to the minus 1/2 x bar minus theta naught squared over sigma squared over n. And I could have just gotten rid of these in the first place. So somebody help me out. Why can I use sufficient statistics and not just the whole data set? How would I prove this? So instead of writing everything down using all of the elements and defining a rejection region over all of the xi's, which is an n-dimensional space that we would live in. So our rejection region is n-dimensional. So where the data has to live in that n-dimensional space before I reject. I can, instead of thinking about that, I can think about everything in a one-dimensional space and think about where x bar lives. That's easier to do. Why can I do that? Somebody prove this for me in 2 words. So I'll give you the second word. It's called theorem. The factorization theorem. So, factorization theorem says instead of looking at this thing right here, I can just look at g tx given theta, that factor right here. So this is going to be theta 1, and this right here is going to be g tx given theta naught. So there is another theorem in the book that says you can do this. Right here, I can bound this thing by k. We got beautiful. So when this is greater than k, I reject. reject when it's bigger than that. This is because of the factorization theorem. So this is the thing where instead of looking at the sampling distribution, informing it in the n-dimensional case, I can always just write down the likelihood function. And I can parameterize my likelihood function with the sufficient statistic. Why? The factorization theorem. So all of those factorization theorem things, you know, they're always kind of obvious. So I don't like using the whole data set. I like to just use the sufficient statistic. And the factorization theorem allows me to do that. So anytime you're working with a likelihood, it's always coming in the form of a ratio, and the constants in front of the likelihood don't matter, because they'll cancel out because they factorize away from each other. So anytime I write down a likelihood, I just throw away everything that doesn't have anything to do with the parameter. So you just toss it. Eventually, if I need to write it down, I'll figure out what it is. I think if you've taken Professor House's class, she likes the term, you hide behind proportionality. You don't hide behind anything. It just is. It's the factorization theorem. So likelihoods are proportional up to something. They're always positive, so they're proportional to some constant. So you throw everything away. You're not hiding, you're making your life easier. Did she say that?
I don't recall.
Oh, maybe not. Okay, so, cool. Never mind. Okay, once you write all this down, this is an example in your book. They give you a slightly different condition. I'm not going to do this by hand, but after some algebra we come up with, you just write this down. So different type of star. Equivalent to this. Probably take 3 or 4 steps of algebra to show this is true. I'll let you work through it on your own. This is x bar is going to be less than 2 times sigma squared over n log k minus theta naught squared plus theta 1 squared divided by 2 theta 1 minus theta naught. So with a little bit of algebra, i.e. canceling out all of this stuff, writing this as one exponential, taking logarithms of both sides and rearranging, we wind up with this. I'll let you work through it. But it's just a high school algebra problem that these are equivalent. You'll notice that if I give you theta naught and theta 1, and I give you k, this is just a constant. So some constant. What you figure out. So what the likelihood ratio test stat, so if we did this with our original density, we would have written down a slightly different constant and calibrated a slightly different constant. Okay, we would have had a constant living between 0 and 1, but it would be equivalent to this. And you can verify that to yourself. So that's just some constant. And because we're incredibly lazy people, we don't like to make our constants look so complicated. So we can make this easier. So this is equivalent to x bar is going to be less than something. some constant. So I'm going to make my constant just look easier. So what Neyman and Pearson are telling us to do, and the likelihood ratio test stat also tells us to do the same thing, is that we're going to create our rule by thresholding x bar, our minimal sufficient statistic. So this is our rule. So if this is true, we'll reject. But Neyman and Pearson tell us to calibrate this test and make sure in the null space, the max probability on the null space, we want to make this level alpha, has to be alpha. So this is what they say to do. Neyman and Pearson say to calibrate this thing. Probability that x is in the rejection region, given h naught, is going to be, we're going to make this thing, we're going to maximize this thing to be alpha. So I want to have the max over theta element of h naught. Again, it's just a point for us, but I'll write this thing down. This is alpha. So this is equivalent to the probability. Our rejection region is defined by this right here. And when you took Stat 101, if you ever took a class like that, you just jump straight into this. Threshold x bar, and they gave you some intuition as to why you do that. What they didn't tell you is the Neyman-Pearson one. So they didn't tell you that that is the uniformly most powerful thing to do. This is the right test stat to use. If you use another test stat, it's different from x bar and you threshold that, you might be doing something that's sensible and reasonable, but if I do it with x bar and I threshold x bar, then in the alternative space, I'll have more power, i.e. I'll have less type 2 error. So I'll do better. So x bar less than c is going to be, I'm going to give myself just a little bit of room, less than c, given our null hypothesis theta naught is equal to alpha. So when the null hypothesis is true, we're going to pick C such that that's alpha. Right there. So we're going to solve for C. Let me make this a little bit different. Give myself just a little bit more room. C minus, actually, let me just keep that written down, given theta naught. And I'll just tell you about something. X bar minus theta naught over sigma over root n, I happen to know a lot about it. I know how X bar is distributed. So X bar is, what kind of distribution does it follow?
Normal.
It's normal. So why is it normal? Well, because the data itself is normally distributed. So sums of normals are normal. Sums scaled by something are still normal. So sum of the xi's scaled by n, it's still normal. This is also normal, right here. How is this distributed?
Standard normal.
Standard normal. You've made an assumption, but it's the same assumption that I made right here. The null is true. So if the null is true, then it's standard normal. If theta is equal to theta naught, i.e. the null is true. So it's standard normal if the null is true. So all of this is equivalent to just looking at this. And I'm going to slightly change my constant, the name of my constant. Sigma over root n is less than C star. You can figure out what C star is. C star is just C minus theta naught over sigma root n. This is just another constant. If I know what theta naught is and I know what sigma is, it's just a different constant. So we can keep transforming this constant, but it's still a constant. Given h naught is true, i.e. theta is equal to theta naught. This we want to make alpha right here. Usually people call this the z-store. It's your standardized value. And so I can pick this thing such that that's alpha right there. And so, for example, let's say I pick alpha to be 0.05. What would C star be? Anybody know? Not 1.96 because you're doing the two-sided thing. So what's the one-sided threshold? So you've done the 2.5% tail. Nobody knows, do they? It's 1.645. I ended up looking it up today. So 1.645 is that threshold. You're not supposed to know this because you're not supposed to be staring at tables all the time. You use your computers nowadays. My generation, we needed to know all these for some reason. So if this was 0.1, this is, I wrote it down, 1.28. So if this was 0.1, if you pick that, then this would have been 1.2. All things that you can just verify for yourself so that you know how to calibrate the test. So that's what I mean. We pick our constant for thresholding to calibrate the test. I could back calculate this and solve for whatever k was if I wanted to. I wouldn't do it though, because it's just a lot of messy algebra. So we usually don't calibrate k. We usually transform it, figure out what the probability distribution of some test stat is, and then calibrate the transform of k. This is just the transform of k, and we calibrate it to our type 1 area. What Neyman and Pearson told us, because we're using this test stat, which is equivalent to using this test stat, we're uniformly most powerful. So we'll beat any other test by doing this. So let me just write down what the power function is for you. You've probably done this before. So our power function is a little bit more general. We're not going to condition on theta naught. So our power function is probability. Let me write this down. It's going to be the probability, and I'll write this down, x bar minus theta naught, sigma over root n. It's going to be less than whatever we just picked C star to be. And this is going to be conditional on theta. So that's where theta pops in to all of this. So I'll throw it into the equation in a second. Let me just ask you a question. How is this distributed? We answered this just a moment ago.
Standard normal.
So we said it was standard normal.
But that's
it's
under,
no longer standard normal.
it's under H0.
That's right. So when theta is equal to theta naught, this thing is standard normal. So I'm going to plug something in that's standard normal. I'm going to just rearrange this. So this is the probability, x bar, and I'm just going to rewrite all of this. This is going to be C star times sigma over root n plus theta naught. Condition on my theta right here. So that's the exact same condition that we had before. I just rearranged it. Now I'm going to subtract off. Give you a little bit more, give myself a little bit more room. given theta. So just rearrange things. Now minus theta divided by sigma over root n. I can't do that to only one side, so I'm going to do that to both sides. So I'll subtract off theta, and I'll divide out by sigma over root n on both sides. This is standard normal. I'll write that down. That's a normal 0, 1. Because we're conditional on theta. And we can see that if we plugged in theta naught, right here, those would cancel. These things would cancel out. You know, we come back to the original thing. The power function is calibrated under the null space. So I'll just rewrite this. This is just going to look like the probability x bar minus theta. I'm just going to write it down like this. This is Z. So it's standard normal. Z is going to be less than, again, that's standard normal. So a random variable is going to be less than C star. Whatever you pick for your threshold, i.e. you came up with alpha, the type 1 error rate, and it's going to tell you what C star is. This is going to be plus theta naught minus theta over sigma over root n. I'll just remind you that this is distributed under theta, but when I write this thing down that that's normal 0, 1, I've said that already, that it's conditional under theta, because that's the thing that's normal 0, 1. So this is that power function. Let's draw it. I'm going to put theta naught right here. Now I'm going to start thinking about this. Is a function over theta 1, where theta 1 is the range between theta naught and negative infinity, I guess, in this case. So what does the power function look like? What we're going to do is we've calibrated it so that this right here is alpha and theta naught. That's what our power function looks like. So let's just kind of think about this. As theta gets really, really big, what happens to this probability? So theta gets really big right here. This is negative, so this is getting smaller and smaller and smaller. So Z, its probability distribution looks like this. This is going to be a 0. This is 1 right here. So this is my normal 0, 1. And as I end up looking at the probability of things that are very, very small, i.e. this tail probability, it keeps getting smaller and smaller and smaller. So as theta gets large, right here, this power function is going to get smaller. You can kind of imagine it does that. And as theta gets bigger and if it gets smaller and smaller and smaller, this number is going to get larger and larger and larger. We pick C star so that this power function goes through alpha at theta naught. This thing is going to get larger. This is going to asymptote into 1. Right here. And this is kind of nice. Because it's a monotone function. So I'll make a point. This is smaller than this is. This is bigger over here. This is in the alternative space. This is in the null space. So let me just write down a condition, and I'll provoke you to think about something. We'll try to tie this all up next time. Saying that, there's a lot to think about here. There's a lot going on. So I'll try to introduce you to some of the controversies. I'll introduce you to one in just a second. So if our power function so I'll say beta naught, or beta prime, right here is in the null space. Beta prime is an element of the alternative space. We say the test is unbiased. These are power functions. So we want the probability of rejecting when the null is true to be small. We want the probability of rejecting when the alternative is true to be large. That makes sense. We wouldn't want it to go the other way around. That would be bad. So that's what an unbiased test looks like. This test is unbiased, right here that we just formed. So it follows this. And we can justify that to ourselves. Here's where all the controversy comes in. Let me just tell you something else real quickly. I'm going to change my example just ever so slightly. Example 2. Here's how my example is going to change. I'm going to flip the direction on the test. So I could go through all the same algebra that we went through before. But this is going to be our power function when H1 has theta 1 less than or equal to theta naught. So that's what we just derived. If I were to derive the power function for this other test, and I calibrate it to be size alpha, our power function would look like this. So this is going to be our power. For when theta 1 is less than or equal to, greater or equal to theta naught. So here's the big issue, is that when I want to test this, example 3, same example, except now we're going to do this. H1, theta is not equal to theta naught. So I'm going to write that out just a little bit differently. So theta is going to be greater than theta naught, or theta is going to be less than theta naught. So the power function pertaining to this and that thing are just these, right here. So you might be inclined to use maybe this power function to test everything. But if you did that, this right here goes smaller than what would happen right here. So let's just say I was only using our first test that we came up with. So I'm only thinking about this right here. If I wanted to test this condition. Our power of the null hypothesis is that. So if I use this first test that we came up with, now the power goes below everything. So it's smaller. So that test would be biased. If I use the other one-sided test to do everything, our test would be biased over here. So what ends up happening is we can't use the Neyman-Pearson criterion anymore. We need to modify it. And so what people will do is they'll modify the test. They'll remove these from each other, and they'll recalibrate C star. So they'll pick Peter's C star, 1.96. What that will do, if I ended up drawing this thing again, is it'll end up making this power function a little bit smaller. We'll still make it go through alpha. So we come up with another power function. It has the same sort of asymptotic properties from test 1 and test 2, but we're going to change what C star is. So we're going to test both tails simultaneously. So Neyman and Pearson no longer hold anymore. What they're doing is they're constraining this and forcing you to take two Neyman-Pearsonian tests and combine them, but only using half of the test on each side. What they're doing is they're constraining the test to the class of unbiased tests by doing that. And so if you ended up using this new power function that we just drew, you can check that the minimal power is at alpha and everything is bigger on each side. And that sounds good. You have an unbiased test. Unfortunately, the rule you just came up with is a non-monotone function. And that messes everything up for us. And so that unbiased condition that you end up throwing in there changes the test to not be monotone. And that's kind of weird. So if you think about the original Neyman-Pearson property, it's this one-sided sort of thing. It looks really appealing. And if the power function is monotone, nobody disagrees with what Neyman and Pearson did. However, by imposing this unbiased condition, everything gets messed up because you don't have a monotone power function. So you piece this together from two monotone power functions and you chop out the part that I just erased down here. I'm going to let you chew on that. And I'm going to come back and I'm going to conclude. I'll also pretty rapidly tell you what a Bayesian does in the point null case. I will not test you on this. So you don't need to study this for the final, but I'll tell you what a Bayesian does, and then I'll tell you more about it if you take my class in the fall. And I'll tell you where the controversies lie there. So Jingden already knows a little bit. Maybe she forgot though. So, but I'll try to allude to it. What I want to point out is this is a major problem in statistics, and we need to do something about this problem. So I'll tell you where we agree, when we don't agree, so on and so forth. But what I want you to focus on in the Neyman-Pearson construction, that if the power function is monotone, no problem. When it's not monotone, I need another criterion. And they talk about that in the book. The non-existence of a monotone UMP test. And so we have to impose a criterion, and we warp everything as soon as we do that. That's it for now, you guys. I'll try to summarize this, but I really think in your statistical careers, you're going to be thinking about this for years. There's full-blown conferences debating what you should do. Hopefully next time I'll tell you what I would do, and the only way to think about this. But there's really no objective way to deal with this problem. So there's only subjective ways you can do it. Imposing criteria that maybe you don't, but there will be repercussions. So anytime there's a trade-off, there's always repercussions. That's it for now, you guys. Thanks a lot. Let me hand out the exams to you as well.